Hello, students. I'm going to go very quickly through the notes that we went through in class today. This is an annotation of the diagram that we've been working with over the past week or so. I'm going to just go through the notes that we took. So this is an already finished set of notes. There's a whole lot of information on here, but if you just kind of follow along, I'll talk about what each of these pieces and parts of information actually are or actually is, and then we'll talk about how we put all of this together as a whole. So what we're going to do here is try to put Kepler's second law and Newton's law of universal gravitation together. So go ahead and put this into your notebook on 1012. Um, we we've been working with this diagram. So this is just a basic diagram. It's an elliptical orbit. Here's the sun, and here is a planet. And so in purple, you have the planet at three different places. Kepler's second law basically says that this planet, as it's moving around through here, in a given amount of time, will sweep out the same area no matter where it is in the orbit. But as long as time 1 is equal to time 2 is equal to time 3, so as long as these times are equal, the areas, area 1, area 2, area 3, those areas will also be equal. Okay, so in a given amount of time, so this could be 1 day, 1 week, 1 month, 1 year, whatever the time amount is, in an even amount of time or an equal amount of time, the planet will sweep out an equal amount of area. So that's Kepler's second law. So what we need to do is tell how that can be. We need to put several things together so that we can explain how or describe how that might work. Because it doesn't just automatically make sense. So how is it that this actually happens? So we have a whole bunch of information in here. So we're saying that this distance right here is T1, and we're saying that the planet is D1, this distance away from the sun. So in this amount of time, whatever that amount of time is, T1 time, this area right here, or this line right here is a better way to say, that is path 1. So that is the path that the planet has traveled. A1, inside here, that's the area that's swept out by this imaginary thread or imaginary line. So there goes the line sweeping, or the planet around, and then the line would sweep. Okay, same thing up here for at position 2. This is time 2, which is the exact same amount of time as here. So if that's 1 week, this is 1 week. And the space in here, this area in here is area 2. The distance away from the sun is D2. And here is the path. That's path 2. All right. And then we're going to look at the third position. So this is T3. So if that was a week and that was a week, then this has to be a week. This area 3, that's a little 3 right in there. So area 3 is the same as area 2, is the same as area 1. This is the path that the planet travels in T3. And so we have all of that information over here. So area 1 is equal to area 2 is equal to area 3. Time 1 is equal to time 2 is equal to time 3. That's all stuff that we've been talking about so far. We're also saying that distance 1 is less than distance 2, which is less than distance 3. And you can see that this is a shorter distance, this is the medium distance, this is the much larger distance. And that's the distance away from the sun. We know that path 1 is pretty long. So in this set amount of time, that planet has moved a long way. So this path is pretty long. So path 1 is long, so it's greater than path 2, which is not quite as long. And then path 3, which is really pretty short. So still a week, not covering much ground. A week covering kind of a middle amount of ground, and a week the planet's just zooming right along. It covered a lot of ground. Okay? So what that tells us then is that this planet has to have a higher velocity. So it has to be traveling faster here than it is here. And then it has to be traveling faster here than it is here. Because it's in a week, it's going to cover a lot of ground here, kind of a medium amount of ground here, and not very much ground here. Okay? So how do we figure this stuff out? How do we start to make some connections? So we have a higher velocity over here. We have a lower velocity over here. Now we also know from Newton's law of universal gravitation that if we have a short distance, we're going to have a large, so if we have a smaller distance, we're going to have a larger force of gravity. So here we have a high force of gravity. And this is because of Newton's law of universal gravitation. So we've got a high force of gravity, and we're going to have a high acceleration. So this just kind of comes from stuff that we've talked about, or some stuff that we haven't talked about, we're going to talk about later on. This force of gravity is pulling the planet toward the sun, but it's moving forward, so it's going to kind of zip toward the sun and then slow down and go farther away. And so that's how we get the elliptical orbit. And you can go back and look at what that actually looks like in your PowerPoint. There's some animations to see what that looks like. Okay. Over here, we have a lower velocity and we have a lower force of gravity, and that's going to give us a smaller acceleration. So that's going to result in this planet not traveling very fast here. So how do we know this distance and force relationship? Well, the way that we know that is because we know that the force of gravity is inversely proportional to the distance squared, or to the square of the distance. Okay, so I just wrote this part, this right here, I just wrote that out for you. Okay, so the force of gravity is inversely proportional to the square of the distance. So if the distance goes down, force of gravity is going to go up. Okay. And then I think the other thing that we need to look at up here is the force of gravity here at 1 is greater than the force of gravity here at 2, and that's greater than the force of gravity at 3. So force of gravity 1 is highest, force of gravity 2 is in the middle, force of gravity 3 is the lowest. Okay, so how do we figure some of this stuff out? How do we use Newton's second law, which is something that we haven't really talked about so far, but that's a little piece that will tie some of this together a little bit more. How can we use Newton's second law in this? Okay, we've already used Newton's law of universal gravitation. How can we use Newton's second law? So Newton's second law says that force is equal to mass times acceleration. Well, our mass here isn't, our planet isn't going to lose weight. It's not going to go on a high protein diet and try to bulk up. It's not going to do any of those things. It's just going to remain at its constant mass. So it's not gaining weight, it's not losing weight. So it's going to be at a constant mass. So if you increase the force, you'll also get an increase in acceleration. If you decrease the force, you'll get a decrease in acceleration. If you want to put in some numbers for that and try it on your own, you can. You can kind of make up whatever you want to if you want to see how that works. What that tells us is that an increase in force results in an increase in acceleration, decrease in force results in a decrease in acceleration, and that is called direct proportionality. That means that the force and the acceleration are directly proportional. So they're directly proportional to each other. Okay? Now, velocity is the next thing. And velocity is related to acceleration. And you can think about this, you're riding with your mom's in a hurry, she pushes on the accelerator on the car, and you start to go faster. You can feel that your car is accelerating, that means you're going faster. Come to a stoplight, push on the brake, the car is decelerating, or it's a negative acceleration, and so the car is going slower. So that's the basic idea here. Increase the acceleration, you get an increase in velocity. decrease the acceleration, you get a decrease in velocity. These are also directly proportional. Okay? So what do we do with this? How can we put all of this stuff together? Well, that's what I've got over here on the side for you. So the basic overall idea is here. There's an increased distance from the sun, and that's going to give you a decreased force of gravity, which is going to give you a decrease in acceleration, which is going to give you a decrease in velocity. So the force of gravity, how do we know this? The force of gravity is inversely proportional to the distance squared. If you have a higher distance squared, you're going to have a lower force of gravity. If you have a low distance squared, then you're going to have a high force of gravity. That's just how this tends to work. So that's a relationship between distance and force of gravity. If you want to insert an example of Newton's law of universal gravitation, this would be a great place to do that so that you can illustrate how this works. Okay? So moving on, what is the relationship between force of gravity and acceleration? If you have a low force of gravity, you're going to have a low acceleration because force of gravity is directly proportional to acceleration. So if you have a low force of gravity, you'll have a low acceleration. So what about acceleration and velocity? If you have a low acceleration, you're going to also get a low velocity. Now, all of this is true for the opposite as well. So if you have a high force of gravity, you'll have a high acceleration. If you have a high acceleration, you'll have a higher velocity. So you can kind of look at this from both directions. All of this ties to the area being swept by the imaginary line. So that's what we're going back to for our explanation. A slower velocity still results in the same area being swept out because the distance is greater. So the imaginary line is longer. A higher velocity still results in the same area being swept out because the distance is smaller. The imaginary line would be shorter. So this is just a set of notes that you can use to help you put together the information that you need to use for the answer to your question. And give me a second, I'll pull that up for you. Here on your next to last slide in your Space Systems Kepler second law set of slides, this is what you are going to be answering tonight on your own. This is not the learning check in and of itself. This is your first attempt at trying to work through this. Tomorrow in class or Tuesday in class, we'll talk through it. I think on Wednesday, we'll actually do the learning check, and then probably we'll be able to move on from there into Kepler's third law. Okay? So, Kepler's second law learning check is going to ask you to use Newton's law of universal gravitation and Kepler's second law to explain the change in speed of a planet orbiting around a star in an elliptical orbit. So basically, how does Newton's law of universal gravitation fit in with Kepler's second law to explain Kepler's second law? So what do you have to have in this? You got to talk about what is Kepler's second law. So make sure that you're connecting Kepler's second law when you're talking about the different components. You're going to have to do the annotation of a model, which we did together in class today. What's the model showing us? How does the speed change through the orbital path? Why does the speed change through the orbital path? How does this change in speed relate to the force of gravity experienced by the object? So connect your Newton's law of universal gravitation equation to what's happening within your diagram here. Make sure that you're talking about the direction of force versus the direction of motion. That's a little piece here. We can add that in tomorrow if you don't pull that in from the animation. And then explain how the areas swept are equal. So make sure that you're connecting your speed traveled and the distance from the sun, kind of that stuff that we were talking about right at the very, very end of the notes that I was showing you. So what you're going to do tonight as homework, so this is Monday night, what you're going to do tonight as homework is just try your hand at this. What are you going to be able to do right now where you are, and what do you still need to be able to learn in order to explain this? because this is what your quiz will be, and then later on, this is what your test will be. The whole idea here is to make sure that you understand Kepler's second law and that you understand how to put the explanation of how Kepler's second law can exist or how it is true. Um, you've got to be able to put that into words. Okay? Hope you're having a good evening. Um, this is a trial. This is not graded, but you do need to try it. You need to be getting this stuff into your mind and kind of like, into a way of thinking about it so that you're ready to ask clarifying questions and to move on to actually being able to do this on your own. See you on Tuesday.